Today from Perth, Western Australia, I am Bandula Samarasinghe, current President of the Institution of Engineers, Sri Lanka, Western Australia chapter. This is the webinar series organized by our Western Australia chapter. On behalf of the committee and the members, I am delighted to welcome you from around the world. Irrespective of the current pandemic, through this monthly webinar series, we have been able to maintain our interactions with our engineering colleagues. These webinars have now become a major part of the annual program of our chapter. This is the third of the series for 2022, which will be presented by an eminent speaker, Dr. Sivaguru Swarnalingam Sridharan from the United States. Dr. Sridharan will be presenting today on the topics of machine learning, quantum algorithms, and data science. Now it's my privilege to introduce Dr. Sridharan. Having completed his high school education at Jaffna Central College in Sri Lanka, he entered the University of Sri Lanka Peradeniya campus and obtained a Bachelor of Science degree in Mechanical Engineering with first-class honors. Following graduation, he started his academic career as an assistant lecturer at the Faculty of Engineering of the same university. Then he proceeded to obtain a Master's of Science degree in Aeronautics and Astronautics from the University of Washington, and another Master's degree and a PhD in Applied Mathematics from the University of Arizona. Dr. Sridharan has held several academic and research positions in several universities and NASA, and currently he is the Chief Technologist of OL Incorporated in Dayton, Ohio in the United States. While Dr. Sridharan has a long, illustrious career in academic management, academia, and research and development, his recently held leadership positions include Vice Chancellor Ramaiah University of Applied Sciences, Bengaluru, India, Provost and Vice Chancellor of the United States Air Force Institute of Technology, Dayton, Ohio, and the Director, Dean of Engineering and Applied Sciences at the United States Naval Postgraduate School in Monterey, California. He has extensively published in fluid dynamics, control theory, and stochastic analysis. Before I hand over to Dr. Sridharan, may I go through the arrangements in place for today's webinar. Dr. Sridharan will be presenting uninterrupted for the next 50 minutes. You are welcome to request any clarifications on the webinar content from Dr. Sridharan via the email address displayed on the screen. Dr. Sridharan will respond to those queries in due course. May I now welcome Dr. Sridharan for today's presentation. Dr. Sridharan, stage is yours.
Thank you very much, Bandula. It's an honor to be introduced by you, and particularly pleasing. You and I go way back, undergraduate days, project team, and friends and so forth, friendship and so forth. It is great to be reconnected this way. So I picked today three topics that are exploding in the scene of engineering and the sciences. The aspects of machine learning, artificial intelligence, quantum algorithms, and quantum computing. And there's a race between different countries, industries to actually build a quantum computer. And even though rather gradually developing the subject of data science. So these subjects are inherently highly algorithmic in nature. So this is somewhat, particularly pleasing for those who are computationally, mathematically inclined engineers, because it's this is the golden era of algorithms and mathematics within engineering, for example. And but it does change the paradigm. So we will discuss these aspects in this talk. Okay, so I also would like to take this opportunity to mention time to time some of our great teachers in University of Sri Lanka, Peradeniya engineering faculty. It's Isaac Newton who said, if I have been able to see further, it was only because I stood on the shoulders of giants. And we were very privileged and fortunate to be selected to study in University of Sri Lanka, Peradeniya engineering faculty, but also be taught by some of the finest teachers in the world. I name 3 of them here. Professor Mahalingam, Professor Bartholomeus, and Professor Ranavira. And I'll mention a few more later on, who inspired me and others to go on to explore further about what we learned in this fine school of engineering. So I could remember in one of the first classes in 1973, in my first year, this Professor Shanmuganathan walks into the class and he was lecturing about, telling us about engineering. It's more or less the first time I was listening something about engineering, because otherwise everything is high school and schooling and so forth. And he said the engineering is a combination of science and art to the utilization of for the benefit of mankind. And but the science, of course, so it's a science and art, a combination of science and art, but the science rapidly changes. Science and mathematics very rapidly change. So how does that rapid change impact our thinking in engineering? For example, what would be the paradigm change in engineering education and practice due to advances in artificial intelligence and machine learning, quantum computing, and data science? If I pose the following 3 questions for us to think about. So what are some of the fundamental developments in machine learning, quantum computing, and data science? And then how do students learn this? If you are going through engineering and then you find that machine learning has become such a household name and has been used in just about every applications in engineering, and quantum computing is that's a technology in which both the United States, China, and other countries, I'm sure Australia as well, are heavily investing on. And when quantum computers become a reality, how do you adjust your computing algorithms, finite element methods, or structural analysis, hydrology, and so forth, when quantum computing computers are available? And data science, of course, you can say that's an evolution of statistics, just like machine learning to some extent. And these subjects may not be taught substantially, at least, in engineering classes. And we didn't study these subjects. We briefly studied statistics in Sri Lanka in hypothesis testing in our 3rd year. And there we saw some probability here and there, but then these are heavily probabilistic and statistical. So how do you adjust the current curricula? So that was my 3rd question: how these modern advances impact traditional engineering curricula, and then also how do these developments necessitate interdisciplinary and multidisciplinary thinking and approach in engineering sciences. So a fresh engineering mind, a student coming through undergraduate and graduate classes. Now, these classes may not have prepared them very well to these subjects. but these subjects are now going to be integral in all branches of engineering. So how what would be the new thinking in incorporating these subjects? So these questions you can think while I go through these three subjects. I do have rather technical slides, but we don't have to go through every detail. I use it just to authenticate some of the words, some of the arguments I make. And in some instances, I will talk in detail. So the topics I wanted to touch, so that someone who is listening to it can go and, these days you can use Google to explore and teach yourself lots of stuff. And so I picked perceptrons and neural networks as one of the topics. Maybe we'll spend some time in detail in discussing perceptrons and neural networks, and I'll speak a little bit about the classical machine learning theory, the underpinning of machine learning ideas due to Vapnik and Chervanen's case. I know Professor Vapnik very well, and is considered the father of machine learning. And we will touch a little bit about quantum computing, the algorithms, and maybe I will just give an idea on what is the difference between classical computing and quantum computing. And one of the major challenges in quantum computing is what's called the decoherence, the interaction with the environment of the quantum system. So this is the open quantum system actually incorporates. We engineers used to think of in terms of thermodynamic systems and control volumes. So think of it like the quantum system can interact with the environment, and so the branch of physics that incorporates the environment called the open quantum systems, and that is associated with a subject that is developed by Hudson and Professor Parthasarathi is in Indian Statistical Institute. This subject, this is here just for completion so that I can tell you, because otherwise people will say, how about decoherence problem in quantum computing? Well, that's why you have this subject, so that we incorporate that well in our discussion. The fifth topic I want to touch is what is now known as big data and the role of geometry and topology. This is because the data can be, in general, in very large dimensions, and therefore well beyond 3 dimensions. So we know how to visualize in 2 and 3 dimensions, perhaps, but in higher dimension we need the tools of geometry and topology. So the purpose is to just to hint. There is a very active branch of big data about bringing in ideas from geometry and topology to throw light into fit high-dimensional surfaces, etc., into data analysis. And so, if not anything, you may regard this talk as one in which we sort of map out the subject areas one need to go and explore, and they are inherently algorithmic and mathematical in nature, but that's the challenge engineering is undertaking now. Okay, so to start the lecture, it was Carl Friedrich Gauss. In fact, after completing his degree in mathematics, he couldn't get a job, which is what's new for mathematicians. So he took a job as a surveyor, and that's how he invented all these techniques that are used in surveying and also in tracking satellites and so forth. But he also invented the least square technique, which is standard in every branch of science. And you can think of least square regression as the first thinking of machine learning. You know, there you have a set of data and you like to fit a curve so that this curve can be now then used as a relationship between the variables, so that when new data come in, you use this curve to predict. And you can even predict in new regions where the data is not available. So that's the purpose of least square, is to come up with the functional relationship that fits a set of data. In the recent times, Frank Rosenblatt in 1957 advanced the famous concept of perceptron. And there was also a Dartmouth University meeting, which is often attributed to the notion that that's when AI and machine learning started. But you know, these subjects start much earlier, maybe started with Gauss or even earlier. So the notion of perceptron would look like this. So you have a set of data points and you like to classify. So pictorially, you look at this graph, and so the purple dots and the green dots appear to be separated. So you like to come up with a curve or a line, in the simplest case, a line. In a multidimensional, it would be a plane, such that it separates the data with some suitable criteria. So if you suppose you are sending this, let's say this data lies on 2 dimensions, and so you are sending a straight line through the origin. In this case, you can actually shift it a little bit or more depending on the type of data, and so that you have a indicator function tells you that for purple data, the indicator function y is going to be 1. You have data here, the y will be 1, and the moment the data is on this side of the line, the y will be negative. So that means that you need to come up with this line and its slope. So a line through origin can be written as W, a vector. I have a habit of dropping the arrow. So think of it like there are arrows here. So it is like W1 x1 plus W2 x2 is equal to 0. Equation of a line. And so this means that you don't know W1 and W2, but if you do know, so what does it do? It so these data come in. Each data you multiply by a weight. W1, x2 you multiply by W2, x3 you multiply by W3, and then so that means that you form this dot x dot W, and then you need a function which simply takes this value x dot W, and if it is it may be numerically, 5 minus 7. So you need to multiply, come up with a function that looks at this and gives you plus or minus 1 depending on whether W dot X is positive, in which case this you are this side of the line, and W dot X is negative when you are this side of the line. So this so that means that if you can somehow compute the W, which is W1 and W1 to Wn for n-dimensional data, then you have a classifier, right? And you all you need to do is to take this dot product, form this function, and then you check this, and it will give you plus or 1 or minus 1. So that's the notion of perceptron. Is the simplest concept of a neuron we have in our brain. So the point is, how to compute this W. So Novikov came up with an algorithm. It's called the Novikov algorithm. It's essentially that you have a set of training samples. So you have the data points and then the corresponding indicator plus or minus 1. you have n of them is given. So they are called the training samples. This is the fundamental notion in machine learning. What you are going to do is to come up with an iterative algorithm. We don't have to go through here, but it essentially defines y twiggle, which is the sign of the xt dot wk. The wk, the weight you don't know, so you want to find it iteratively based on the training sample that is given to you, right? So you come up with an iterative algorithm. Iteratively, you correct. You start with, let's say, 0, and then check the sign of this dot product, right, and then you either add it or you don't do anything, right? So it's an algorithm to find the your learning. This is the first example of what machine learning people call a learning function. So you come up with this line, and which can be used later on in other data comes in. So, but the point is, not even without paying attention to the algorithm, we'll say, will this algorithm converge and give me a W? So there is a theorem, it's a famous, it came in 1962. So original Perceptron by Rosenblatt and Novikov's Convergence Theorem, which assured that the perceptron iteration would converge, were the two things that got the machine learning going. So that essentially says you don't have to read the full technicality. That the last line is what is needed. So that the perceptron algorithm makes at most finite number of errors. So this means that you keep iterating this one, and then it converges in finite number of steps. And so that you don't keep this means that you have a set of training sample, and you can calculate the learning function. Now you are ready. So now the neuron is represented by this learning function, and that is the point. Okay, and and then immediately after those two work, there was an explosion of activities, and people said, okay, instead of this one layer of inputs and this neuron here, how about many layers? So they came up with the notion of neural nets. So so here neural net consists of is a picture which I have 3 layers drawn, 2 hidden layers as it's called. So here I say that a neural network contains n+1 layers. The first layer describes the input vector. Remember the input vector we came in the perceptron example, right? That's the input vector. And so here, since it has many layers, then we need to come up with another variable. So we say it is 0, so as at the input level. When the number of layers are very large, then a neural network is called deep neural network, DNN. So that is the quintessential machine learning device that is used today, and it is as simple as this. So the point is, now earlier we had to worry about what is this weight or the slope vector, right? Two variables, W1, W2 in the picture, n variables here in the single layer problem. But here in the multi-layer problem, so each layer has weights. So you have a weight matrix that need to be calculated based on your training samples. So that was a big problem in the 60s, and it was resolved by what is called now called the backpropagation algorithm. It's so important and fundamental. So let's take a few minutes to spend on it, and then I will tell you what this means. So the you think of the image of the input vector on the kth layer. Once you get to the kth layer, maybe first layer, second layer, you keep mapping it. Would look like x1 to xn k. So what do you do? What did we do here in the first perceptron case? When the input vectors come, each of them multiplied by this vector, we form this dot product. And then we need to come up with a function which takes this dot product and give you a plus or minus 1 type answer. So, what happens is you form this, now it is a matrix, W is a matrix, you multiply by your vector at k minus 1 layer. And then you need a function which what we call a sigmoidal function. A sigmoidal function is nothing but something is when the argument is minus 1, minus infinity, it is 0. It is when the argument is plus infinity, it is 1. Instead of just a step, giving plus 1 or minus 1, it just smooths out. Examples of sigmoidal functions I just write here. There are many functions which looks like smoothly starts 0 and then climbs to 1 and becomes 1. So what does it do? It plays the same role of this function f, which takes this dot product, which is a number, but it is not necessarily plus or minus 1, but it signifies either positive or negative. So we just need plus or in this picture I put minus 1 and plus 1, but the sigmoidal function can be just it gives you 0 and 1. So at each layer it sort of smooths out and gives you minus 1 or plus 1, 0 or 1, and then you go to the next layer. So that's the algorithm for a deep neural network. You essentially took the idea of the perceptron and you duplicate that to n layers. Even n can be 20,000. In some of these, you can now go and read about deep neural network and Google's deep mind. When they say deep, this is what it is. There are so many layers, and this means that there's a big challenge of calculating these weights. Once you have computed the weights efficiently, then you have a network like this with all the weights are known. So the new data come in, you can do calculations. So what do you do? In order to calculate the weights, what you do is you go to the very last node here, and so this is the indicator function. This is the output from the deep neural networks, neural network at the mth layer. So you find the difference, and you form a least square. You square it and you sum across all the. So what did I put as L? L is so the number of steps you had here, right? And sorry, the number of points in the data. So you had to square it across, sum it across all the points in the data, and so that will give you your weights, subject to constraints, because these least square constraints. The constraint is simply this relationship I showed you, that at every layer, you take the whatever the value each of the previous node is injecting, you multiply by the weights, corresponding weights, and then you apply the sigmoidal function. And so this is and then you get the value in the next node. So then, and therefore this is put as a constraint. So this is like a typical Lagrange multiplier problem in finite elements or numerical analysis. And so you have a constrained optimization. So what do you do? How do you handle the Lagrange multiplier? You take this guy, and then you want to put these constraints with a Lagrange multiplier BI. You sum over, and then now you need to minimize over all the weights, all the nodal values and all the multiple Lagrange penalties B. So this means that how do you find the minimum? You differentiate with each one of these matrix variable, vector variables, right? And then set them to 0. So this is what we study in undergraduate and in grad school. So that gives you a set of equations. I'll give you the ultimate result. So after the calculation, the whole goal is to find find the weights, just like the Novikov algorithm. For deep learning, you do what is called a back propagation algorithm. It was a big hit because the calculations only depends on the previous step. So you have a forward pass. So you have an first iteration of the weights are known, or you start with some weights value. And so you have a forward pass. So you start with the initial data and you do for all the steps and for all the inputs. So that will give you the first iterate. And then you go back in, you go backward. You go back, first you go forward with the first iteration values of these W. Then you update your, you find your nodal value, then you go back. So that's called backward pass. And then during the backward pass, you compute the Lagrange multipliers B from known values of from the previous calculation of the weights and the known values, the nodal value, which the previous iterate. Then you come and do another update of your weights because now you have calculated the B, calculated the previous W's. Now you come, you update the weight. So this is called a backward propagation algorithm, very, very famous in machine learning. These are, so what I just described, Perceptron, the shallow or neural network. The notion shallow and deep is only on how many layers you have. So it is not a scary thing. It's just that you have many, many, many layers. They use the word deep neural network. And you know how to calculate the values W, right? Here using Novikov algorithm, and here using back propagation algorithm. And there's an issue about whether the one criticism about deep neural network is that this is because of the sigmoidal function is not convex, and therefore the minima is not unique, and so you will pick up one of the minima, and that's not unusual in engineering. You have non-convex problems. You know, there are some theorems saying that, well, one hidden layer is adequate, but no control over number of neurons. But at this discussion, you know, I just put that as a footnote. Okay, so that you know, I managed to at least speak about a very big topic today, the deep neural network, and armed with the notion of perceptrons, Novikov algorithm, and the back propagation algorithm for deep neural network, a student should be able to pursue and even implement. You know, there are Python codes that implement this, so you don't have to agonize through. You just need to know how to use the Python, which or TensorFlow. The notion tensor is because these W's are, you know, is a matrix and therefore is a tensor. So you need a rapid way of calculating this W. So an undergraduate student, if he or she needs to use deep neural network, what he needs to do is to learn Python, which implements back propagation algorithm, and just need to know, you know, what is that he or she is calculating. Okay, but so this doesn't involve any physics. So it doesn't tell you where this data are coming from, right? And the goal is that if you don't know anything about the underlying physics, underlying dynamics, underlying chemistry, Then you just have a set of data, and then you train your neural network. You know the weights. So everything about the neural network is now known. And then a new data comes in, and the neural network will predict, what should be the output WG. And people have gone a step beyond that. Suppose some aspects of the physics is known, like you're watching a combustion inside a combustion chamber, or fire propagation, or many other applications, where you may be able to come up with the model equations, but not all the parameters are known. So in a situation like that, can we incorporate some aspects of physics, or what we know about the physics, into this deep neural idea? So that brings us to the idea of incorporating physics into machine learning, or physics-informed machine learning. Here is the former president of United States holding a T-shirt. I think he must have attended a conference which has the equations of fluid mechanics, Navier-Stokes equation. So I was very proud of this photo. I am showing it. So that's an equation, for example, is very much at play, because it's very difficult to get, almost impossible to calculate fluid flow characteristics at very high Reynolds number, or other parameters. And but then there are other branches of physics. So I recall two other inspiring professors from University of Sri Lanka. As Professor Jai Telaka, our thermodynamics teacher, often used to tell me that complex physical problems in engineering are often beyond the reach of theoretical approach, because he knew that I like to go down the path of theory. So he was an expert in boiling heat transfer, which is not accessible to theoretical treatment even after 40 years now. So he was right in his viewpoint, but nevertheless he became theoretical and computational person. But he was an inspiring. And then Professor Thurraja, from under whom I didn't study because I was a mechanical engineering student, but he was very well known for constitutive modeling of in soil mechanics situations. There are constitutive relations named after. It's essentially like stress-strain relations. Hooke's law is the most simple, linear, and then there are more non-linear relationships. But if you look at soil, there are other heterogeneous media where the stress-strain constitutive relation is beyond theoretical reach. So you come up with empirical models, and but these are also candidates for our machine learning ideas. For example, you can think of Thurraja's constitutive relationship as an example of a learning function. And likewise, if somebody gives you a problem in boiling heat transfer today, even today you had to rely on data only, and perhaps machine learning to throw some light into the subject. Okay, so I just quickly say what do you do in if you want to incorporate more physics into the problem. For example, you have equations of fluid flow. I didn't write down the equation, but it's a set of partial differential equation with initial and boundary condition. So if you substitute the output of the deep neural network, I denote it as phi, that depends on the data, whatever the time you are, because in the calculation I showed there was no time, but you can include as an additional parameter, and the weight functions. Into the equations of fluid mechanics, you get it won't satisfy, because the neural network is not a fluid medium. So it gives a error. And so we call that a residue. So what we can do is, in our previous Lagrange multiplier, which we had this for the neural network, you add 3 more loss functions, as they are called. And there are these errors in the errors we had encountered here. and error similarly doing in initial and bounded data. And you form this the full Lagrangian, and then you do a Lagrange multiplier for this the whole problem, and that is called physics-informed neural network. So it's a step beyond the current deep neural network. It's a very active branch of research, and someone is interested, you start with your own model, whether it's hydrology or combustion, and then you can take the deep neural network to the next level, as is done in this research. Okay, now we move on to some theoretical underpinnings of machine learning, and that is actually due to one of the pioneering scientists in machine learning theory is Professor V.N. Wapnick. In fact, the notion of VC dimension is that V here. He advanced many aspects of machine learning. So he often points out what is the difference between traditional statistics and machine learning. Because you may say that they are all traditional statistics. Also, you have a set of samples, and then you form means and variances, and then you use that. And when as the sample size get larger and larger, you expect the underlying dynamics or population or whatever is to be estimated and predicted. The difference is that here you deal with a finite, a small number of samples, fixed number of samples, which are called training data. And you don't have, well, you can actually increase the sample size, the training data as you move on. After all, that's how we learn what's called experience, human beings, right? Our the learning function keeps better because we get a better and better training data as life progresses. So there's a fundamental difference that the training data size is fixed and it can be very small. So let's spend a few minutes on Wapnick's underpinning of the subject of machine learning. So right now, I go back to the foundation of the machine learning. And so the problem of machine learning is that you had to find a learning function. So very much like here, we go back all the way back to the simplest case, where we have a learning function, or that is given by the neural network. And so we need to come up with a learning function, which from a class of hypothesis class, which we call alpha. And so once you design the learning function, you like to predict the future possible, when something comes along, what should be the response. So the selection of this learning function, as we did in the case of neural network and perceptron, is based on a set of training data, which is called L, was the number of input I had, just like in the previous case. So we have L random, independent, identically distributed observation, very much like statistics. This means that all data are coming from the same probability distribution, and they are statistically independent. So that's an assumption you have in the statistics. There is an assumption you have in machine learning. And so you have what's called a training set. So the data x1 will have a response y1. It could be plus or minus 1, like or 1 or 0, depending on how you come up with your indicator function, the output. And these data are actually coming from a probability distribution, right? And the hypothesis said, so the class of functions, learning functions that's available to you can be finite or infinite. And so what we did, just like in the least square, is that we formed we summed it across the input, just like in this example, we summed it across the input. And then now we seek to minimize the empirical average, so that we can find, we can select the minimum, the alpha naught, so that gives you the learning function. Okay, so this is called empirical risk minimization principle. Examples are, one example we just saw before in the case of deep neural network. You have output, and the this is the indicator function. This is the output from the neural network. So the sum, least square sum, we minimize, or it could be maximum likelihood, like its statistics. And I just spend 1 minute on the notion of BC dimension, and not the abstract definition here. So BC dimension essentially is that you come up with a certain hypothesis function or classify how many points it can classify. So that tells you what is the BC function. So if suppose you're on the plane, think of it on the plane, and you are going to come up with these lines, and these just like the perceptron form. So what is the BC dimension of a plane? And half space like this one, you draw a line, you say 0 on one side and 1 on the other. So if you have 3 points, if I color them differently, then you know that there is 2 to the power 3 ways we can differently color them. And according to that, you have if you have simply a line, notice that it classifies all of them. It separates all 3 red. It separates the red here. It separates the red here. Separates the red here, here, here. And if there's no red here, it's so it open half space classifies shutters. We call it shuttering. Is 3 points. It's called BC dimension is 3. If you have 4 points on the plane, 4 data points, one line can't separate, because the points can be of this form where you have 2 red and a blue on that side. You need 2 lines to separate, and therefore the BC dimension is 3 and not 4, because so that's a way you quantify the hypothesis class or the learning function class on how they can separate the data. Okay, and I can skip this, but this is one way of estimating what happens to the real scenario versus the empirical scenario. I skip I just say a few words about the spin glass dynamics. So neural network and Vapnik-Chevaninski's theories. So they started in the 60s. So they gave us even the concept of neural network, the back propagation algorithm, and so forth. And then also a number of years ago, a number of people pointed out that you can bring the idea of coming from statistical physics, a notion of spin glass, which I don't propose to go through here, but just to let you know that there's a way of converting neural network to a time-dependent dynamics and study its statistical properties. So that is the subject of spin glass. It's also quite popular these days as well. If you have a very large dimensional, very deep neural network, 50,000, so you want to understand its properties, behavior, also statistically. And so the notion of spin glass was brought in so that you bring some dynamics into the problem, and they prove many characteristics. So I threw through slides, 2 slides there. Okay, now we go to the next topic, and it's the topic of quantum computing. The point was that Richard Feynman pointed out, originally he was is interested in simulating quantum physics with computers, and he argued that you cannot do that with classical computers. So he wanted to advance the notion of quantum computers, but now it is has evolved into a new computational algorithm, and the computers are, people are trying to build with large number of qubits, and so this is one of the key papers in quantum computing, in Feynman's original paper in 1982. So that sort of sets the start of the subject. There were other people who contributed it. The things you hear, and I will also point out, are things like show algorithms, Grover algorithm, quantum error correction, quantum Fourier transform, the notion of entanglement. I had slides in there, I removed it. So first, in a nutshell, what is the difference? A classical computer, it's the classical bits are either 0 or 1. Whereas a qubit, a quantum bit, it's in its simplest form, it's actually A times 0 denoting a vector, and B times 0, 1 denoting another vector, and with A squared plus B squared equal to 1. So in a simplest perspective, you can say that the qubit has more information because of this latitude between A and B, and also you can have it's not just one vector but multidimensional vectors. And originally this is the quantum wave function. So in order to understand that, we need a little bit of language, and so it goes like that. Suppose you denote, this is the famous direct notation. If you denote the column vector this way, it unfortunately this is called Bra and Ket, and so this bracket notation, and so this is a column vector is denoted this way, a row vector is denoted this way, and therefore a dot product is denoted very nicely this way. And the dot product will satisfy the usual properties and not proposed. Here and the row here, then it will form a matrix. And likewise, you can also define an outer product with 2 columns, 2 vectors, and then if you multiply them, you get a mn dimensional vector. So this gives you, this notation gives you more latitude, and it's much simpler to work with, because just by putting this, you represent a matrix here. Just by putting this one, or introducing a multiplication operator like this, you introduce a column vector. And a qubit, as I mentioned before, is a sum of these 2 vectors. And in the simplest case, the vector can be the 0 indicate 1 and 0, and 1 indicate 0 and 1. So these 2 are orthogonal that way. And alpha squared plus beta squared is equal to 1. A quantum register is actually a multiple qubit. So for example, Psi2, that's where physicists get very brave with the notation, is if you have n is equal to 3, in binary, you will have these 8 vectors, these 8 vectors. So all the binary number expansion of 2 to the power 3 will take this shape. For example, if you have a number 5, I just wanted to see how to do binary expansion. 5 is written as 1 times 2 squared, 0 times 2 to the power 1, and 1 times 2 to the 0. And hence 5 is actually denoted this way, binary form. But this is deceptive, because this is what you actually mean by this notation. Is that it is these 3 outer product, and that's this big vector. So this big vector of 8 entries is simply denoted either 5 or this way, 0, 1. So that's the brilliance of this Dirac notation. By the way, there's a famous Sri Lankan mathematician, Dr. Eliezer. Actually, he got his PhD under Dirac. So just to mention that. So what do you do with this? So you only need to learn, you don't need the entire quantum mechanics, that operations in quantum physics are in terms of unitary operators or unitary matrices. That means that you multiply a matrix by its transpose, you get a unitary matrix. And that is the nature of Schrodinger equation, how it propagates the initial data to a time. And so that is manifested into in the finite dimensional quantum computing situation. You deal with what is called unitary matrices. And the simplest unitary matrices are called polygates. So what they do in quantum computer is regard these matrices as operators acting on a particular state, and you translate that to certain gates, and so there's in the quantum circuit, and then you can design quantum computers that, and so the polygates are matrices of this type. I is a complex number, and they have the properties x squared and y squared. They are symmetric matrix, antisymmetric here, but they have this property. Yeah, this one will be Hermitian when you so this we may take the transpose and conjugate. So they are Hermitian matrices, symmetric for the real case, and so they are unitary matrices. These are the simple. So the unitary matrix X is called the NOT gate, because if you apply X, this matrix, to 1, 0, remember this is 1, 0, it will give you 0, 1. And a simple calculation would solve. And likewise, if you apply the X gate or the X matrix to 0, 1 vector, it will give you 1, 0. So it is X is called the NOT gate. Likewise, you get Hadamard gate, which is 1, and then this thing is not. I need to. Okay, so this is sort of covering, so I don't know how to get to this. Hadamard gate essentially takes a simple vector and it mixes. It gives you a combination, and that's what is underneath there. Similarly, you can actually define n-fold Hadamard gates, and a phase gate also. It changes one vector to I times 1. And then you can define another what's called a pi by 8 gate this way. It changes the phase. And then there is something called C0 gate you come up with. So what do you do? So this means that you have a bunch of 2 by 2 unitary matrices, and there are certain gates associated with them. That is the lesson in this. So, and then the entire quantum computer is based on these 2 by 2 matrices, and these gates defined based on these 2 by 2 matrices. And so that is summarized here. in classical computation, the AND gates, the OR gate, and the NOT gate are universal, means that any Boolean operation can be realized using only these three. So the quantum analog of that, I stated as a theorem here, but it is summarized here, is that quantum analog of this theorem is that any unitary transformation, any quantum action of an n cubic can be approximated by composition of Hadamard gate, C0 gate, phase gate, and phase gate to any degree of accuracy. So this means that any quantum operation can be designed in terms of these simple gates representing 2 by 2 matrices, and that is the lesson in quantum. So in quantum, the moment you go from classical computing into quantum computing, the lesson is that now all your thinking is in terms of these unitary matrices. Fortunately, that big, large unitary matrix operation can be broken down into 2 by 2 unitary matrix operation. Okay, so that is a sort of a brief introduction to the notion you need to first learn when you learn about quantum computing. And so here are some of the major developments in cryptography. And the first one is called Diffie-Hellman public key exchange. The other one is RSA algorithm. The third one is called the elliptic curve cryptography. And they all have computational complexity associated with them. And so they involve either factorization. So the challenge in breaking this encryption, RSA is typical in our credit card. The elliptic curve cryptography is also a competitor. Is that discovering a prime factor can be challenging once the number of digits become large. The prime numbers are like 2, 3, 5, 7. The numbers which cannot be written as a product of two other numbers, prime numbers. So 15, I give you 15, you can write it as 3 and 5. But if I give you a 15-digit number, you may need years and years of computer time to come up with a prime factor. So that challenge is incorporated into encryptions, and that's why your credit card number is 16 and so forth. So prime factorization is hard. Likewise, discrete logarithm in the discrete field, ones and zeros, computational complexity gets immensely large. So that is so then the question is, will the quantum computing make a difference? So in 1996, Peter Shaw showed that he uses the fundamental notion called hidden subgroup. That's why I wrote it there. He can do prime factorization, which was key to Rsa algorithm. Can be done in polynomial time steps and also discrete algorithms, so discrete logarithms. So the two of the most quintessential encryption algorithms, the RSA algorithm. RSA is because it's due to reverse Shamir and Edelman. And this is elliptic curve cryptography is due to Neil Koblitz and Victor Miller. And it can be done using polynomial in the number of steps only grows polynomial in time if you use a quantum computer. The type of calculation we just went through. If you, instead of the classical computer, you work with quantum gates, which operate in terms of unitary matrices. And so that was a big breakthrough. So it says if there's a quantum computer, then it can break in reasonable time all the credit card numbers, all the current encryptions you have. And therefore, it's a major threat to the cyber security worldwide. And that's why the quantum computing is such an important subject, that algorithmically, these mathematicians and computer scientists have shown that if using quantum algorithms of the type I described, you can the effort, algorithmic effort only grows polynomial in time steps instead of exponential in the classical computer. And therefore, it's a major threat. If somebody builds a quantum computer first, that country will break every other country's all the banking systems, and so that's why building a quantum computer is such a fun. So I mentioned, but there are many obstacles in building a quantum computer, and one of them is interaction with the environment, and what's called the notion of decoherence. And so that subject has been studied, and one of the leaders have been Professor K.R. Parthasarathi, currently in Indian Statistical Institute. He's sort of retired now, but scientifically active. And so I just wanted the historic significance I wanted to show. I had some slides on the quantum, his subject, but we can skip over. And talk about two other subjects. And the two subjects I want to talk, one is called geometric, so at the beginning I said I want to talk about traditional machine learning. So we spoke about neural networks, deep neural networks, some aspects of Wapnick theory. These slides are complete, so we can pass on the slides, and you can the audience can explore further. And then I spoke a little bit about quantum computing. I did spend a little bit time on trying to orient the audience to the some of the direct notations, and then the 2x2 matrices you get in unitary matrices. Then the big theorem is that any unitary matrix representing a quantum action can be represented as a product of 2x2 matrices, and therefore 2x2 matrices can be mimicked by quantum circuits, 2x2 unitary matrices, and therefore you can theoretically design a quantum computer. But the building has its own challenges. You hear news announcement in just about every posting in LinkedIn that somebody is building a quantum computer, and with a large number of qubits. That's what they will say, right? So the dimension of qubits is how many. So I showed you some examples of qubits, like this. This is 3 qubits here. They say now 48 qubit, 50 qubit, and so forth. So we need a large number of. There are computations to show what should be the size of the qubit to do a typical calculation. So I'll invite you to read about those things. And the direct notation is you sit down and go through, and you'll find that it's trivial, and just that it's a matter of convenience. If you don't learn direct notation and try to learn about quantum computing, you will find that it's a nightmare. So spend an hour on learning about direct bracket notation, and you'll be fine. The third topic I wanted to touch is the role of geometry in understanding data.
Excuse me, Mr.
Yeah.
Srisaran. Yeah. I think the time is almost up. Can you go fast or do something like that?
Okay, so I'll just use 2 minutes or something to summarize.
Okay. That's fine. Yeah, we'll edit this part. Yeah, don't worry.
Yeah. Okay. So So the yeah, there is some things you can edit. So there are two subjects I wanted to talk about. I think this one slide is enough to show that. One is called the geometric evolution. This young professor in University of Sri Jayawardhanapura, she works on Wilmore flows, and her name escapes me. So there are, it propagates various surfaces to understand physics: flame front, liquid crystals, and image processing in the case of research in Sri Jayawardhanapura. And the other topic is how do you embed a surface inside in a large dimensional set. So I just go and show these two slides as the last slides. Everybody would have seen the movie A Beautiful Mind, a story about Professor John Nash, whom I hosted, for example. He died in an accident a few years ago, Nobel laureate in economics, and Russell Crowe playing the role of Nash. And his biggest contribution, one of his biggest contribution is that if you have a higher dimensional surface, n-dimensional surface, a surface is curved just like a sphere. So can you imagine an Euclidean space so that you can give Cartesian coordinates? So that's called embedding. So if you have a surface in n dimension, can you find a larger dimensional Euclidean space so that you can have Cartesian coordinates, n coordinates to describe this surface, so that you have thinking reversely, if you have data in n dimension, can you find an n-dimensional surface without distorting? And he actually, that was one of his famous theorem. It's called the embedding theorem, and this is him describing, and he showed that this is possible. And this type of ideas are now becoming important in big data science, because we want to understand data in high dimension. And so scientists are thinking about how they can utilize results like Nash embedding theorem. Okay, so that sort of ends my talk. I wanted to touch three big topics. All three of them have a highly algorithmic nature, but they are, this is called in some sense disruptive innovation that happens. These subjects have been developing in many different disciplines within engineering and sciences, but now it's centrally at engineering for us to use in understanding large data, in designing deep neural network, or utilizing quantum computers as they are built in calculations which are beyond reach currently. So this is the message I want to convey, and I thank you, the organizers, for your kind invitation to present this talk. Thank you.
Many thanks indeed, Dr. Sridharan, for your insightful and thought-provoking presentation. We are sure our listeners today have enjoyed the presentation and benefited from it. As mentioned earlier, our listeners can send your queries to Dr. Sridharan via the displayed email address. We also extend our thanks to all listeners for your participation. The next monthly webinar scheduled for May will be on a mining engineering topic, and the details will be brought to you soon. See you next time. Stay safe. Goodbye.